Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 13, 2026, just about 6 days ago. It reveals that popular group-based reinforcement learning methods actually suffer from a fundamental mathematical bias and proposes a solution called HADW that improves performance on hard math problems by over 3%. The paper is titled, "Your Group Relative Advantage is Biased," and as we'll see later, the implications for how we train reasoning models are quite significant. Alright, Figure 1 summarizes the paper's contributions, starting with the performance gains on the left. Panel A compares the proposed method against baselines across 5 math benchmarks, showing that the new approach, HADW, consistently outperforms standard algorithms. In the middle, Panel B visualizes the core bias issue. It demonstrates that for hard prompts, current methods drastically underestimate the advantage compared to the true value found with more rollouts. This explains the result in Panel C on the right, where the radar chart shows the largest improvement, over 3%, specifically on hard reasoning tasks. So Theorem 1 provides the formal mathematical proof of this bias. It establishes that for any group size greater than 2, the advantage estimator is not neutral. The first equation at the bottom shows that for hard prompts, where the success probability PT is less than 0.5, the estimator is systematically lower than the true advantage. Conversely, the second line proves it is higher for easy prompts, causing the model to over-prioritize simple tasks while neglecting difficult ones. Well, Figure 2 plots exactly how severe this bias gets depending on the problem's difficulty and the group size used during training. The horizontal axis represents the success probability, ranging from extremely hard tasks on the left to easy ones on the right, while the vertical axis tracks the magnitude of the estimation error. Notice that the error is 0 only right in the center, at 0.5. As we look at the top dashed line, which represents a group size of 2, the bias spikes dramatically at the edges. Even with a group size of 8, shown by the bottom red line, significant bias remains for the hardest and easiest prompts. While Figure 2 quantified the bias, Figure 3 presents the solution, the history-aware adaptive difficulty weighting framework. The bottom section shows the first phase, where the system tracks an evolving capability state using a history batch labeled C1 through Cn to establish a stable difficulty baseline. Above this, the dashed box details the correction phase. As the dials indicate, the algorithm boosts the advantage signal for hard tasks to encourage exploration, while dampening it for easy ones to prevent the model from over-exploiting simple answers. Okay, Figure 4 tracks the actual training dynamics to see how this reweighting changes model behavior over time. Across these 6 panels, we monitor accuracy, rewards, and response length for models of 2 different sizes. If you look at the first 4 panels on the left, the solid lines represent the proposed method, while the dashed lines are the baselines. You can see that the solid lines consistently climb to higher plateaus in both accuracy and reward, indicating better convergence. However, the key insight lies in panels E and F on the far right, which track the length of the model's responses. Here the solid lines stay significantly higher, meaning the model is learning to generate longer, more detailed chains of thought to crack those difficult reasoning tasks. So, having seen the training dynamics, Table 1 now lists the comprehensive results across 3 different language models. The table tests the method on top of 3 base algorithms, GRPO, GSPO, and DAPO. If you look at the top section for QN34B base, the rows marked with plus HADW consistently show higher scores. For example, applying it to GRPO lifts the average accuracy from roughly 46% to nearly 49%. This trend repeats in the middle section for the 8B model and the bottom section for Llama 3, confirming that the gains are robust regardless of the underlying architecture. Wrapping up, 2 takeaways stand out. First, standard group-based methods inherently punish models for trying hard problems due to biased math. Second, fixing this with adaptive weighting doesn't just improve scores, it actually encourages the model to think longer and deeper. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.